This is video 269. I'd like to go over apparent depth. This is just an application of using Snell's law that we just talked about in the previous video. You're probably aware that whenever you put an object in water, it looks closer than it really is. You can see that in this ruler here. You can see it when you put a pencil in water and then it appears to bend. This occurs because light is bending when it enters from the air into the water. Let's take a closer look at what is actually happening here. So your object is really here. So this is the actual depth of your object. The rays are originating from the object as we talked about previously. So they are originating from the object going this way, and then they're bending away from the normal as they move into the air from the water. We learned that we see objects when these rays of light come into our eyes. So our eyes don't know that these incoming rays, that they bent at this boundary here. Our eyes, what they do, our brains, they trace these rays back and they assume that they assume that the object is at the location where all of these rays intersect backwards. So that's where we see the image, where all the rays intersect. We're going to do a lot more on this when we talk about lenses and mirrors. But that's why when you project all of these rays backwards, they all intersect here. So the apparent depth is a lot closer to the surface of the water than where the actual object is. So it turns out that you can use Snell's law to figure out exactly how this actual depth here compares to the apparent depth. We're not going to go through all the math. I used to, but it's a lot of geometry and it requires a small angle approximation. But if you write down Snell's law and find the ratio of these indices of refraction here, it turns out that this ratio of indices, you can divide this by sine of theta 2 here, is equal to the ratio of the apparent depth over the actual depth. And that comes from geometry because these angles 1 and angle 2 here are over here. If you look at one of these rays and you draw that normal line here that's perpendicular to the surface, you've got that tiny little angle 1 here, and that little angle 2 over here, and those angles end up being related to the size of these triangles here that can be formed. So I'll spare you all the details, and we can just use this equation directly to figure out what is the apparent depth of an object if we know the actual depth and the ratio of the indices. So which one is number 1 and which one is number 2? Well, since the ray is incoming from the water, that means this is N1 over here. And then the ray is outgoing over here into the air, that's going to be N2. Let's do an example where we use this equation. In this example here, it says that a fish appears to be at a depth of 120 centimeters. What is the actual depth? So you can see here, slightly different picture, but the fish is really here. But when that ray of light exits the water, it bends this way, it refracts away from the normal. And then our eyes, when they look at this ray of light, they project it backwards in a straight line, and that's why the fish appears closer than it really is. So let's write down the equation that we just learned about. The apparent depth is equal to the ratio of the two indices multiplied by the actual depth. And what we're looking for in this problem is the actual depth. So let's go ahead and solve for that. The actual depth, I'll just write it actual, is equal to n1 over n2. I have to multiply by the reciprocal here times the apparent depth. So let's write down our numbers. N1 is the water here, and we're going to use a value of 1.33 from our table earlier. And then N2 is the air, and that's always equal to 1 for the index. And the apparent depth was 120 centimeters. So when you multiply 120 by 1.33, we're going to get an actual depth of 160 centimeters. So this was just an example of using Snell's law, and we're going to do more examples in the following videos.